Okay, this is going to be the video for Calc 3 section 15.7 on cylindrical coordinates. So this is triple integrals in cylindrical coordinates. This is a much shorter video than the last section because it's just based on the idea of polar coordinates. So we've already kind of seen that, and there's a lot of different ways things can come about. So we're just going to do a couple of representative examples and then answer most things based on doing homework questions, okay? Not in the lesson, but in the class. So let's talk about how cylindrical coordinates work. Cylindrical coordinates is one of two different ways that we can alter triple integrals to make them easier to evaluate. The other one is called spherical coordinates. We're going to talk about that next week in section 15.8. But remember when we had double integrals, that the typical way to express dA dx, or dA is dx dy, right? But we said that whenever we had something which was circular, rather than dealing with the square root of 1 minus x squared or those kinds of things, it's sometimes more advantageous to define things in terms of polar coordinates, right? Where we said that we have a radius at a specified angle counterclockwise from the x-axis. And that means that the x-coordinate is the cosine of the angle, actually times the radius. This is a typo here. This is r cosine theta, and sine is r, and y is r times sine of theta. Okay, where r is the square root of x squared plus y squared, and then the angle, since the tangent of theta is opposite over adjacent, it would be r sine theta over r cosine theta, which is sine theta over cosine theta, which is tangent. So the angle is just the inverse tangent of the y component over x. So you can either convert from rectangular to polar, or you can convert from polar to rectangular, r cosine theta, r sine theta for x and y. And that means that the dA, instead of being dx dy or dy dx, is r dr times d theta. And we talked about why, because the one dimension is an arc length. To convert, you have to use r d theta to make that times the dr. So we get r dr d theta for polar for the dA element, okay? So for triple integrals, we're going to have another element that's similar. We're just going to say, let's say I'm doing a triple integral of some function of x, y, z. Normally we would have things like dx, dy, dz, dy, dx, dz, and the 6 different ways for that. But if in one of the planes there is a circular cross-section, or anything that involves a circular cross-section, even including cones, then it's more advantageous to leave one of the dimensions linear in rectangular, but to take the other 2 dimensions and replace the linear with polar coordinates. So arbitrarily, I'm going to say, let's say that z is the direction which is the kind of axis of rotation, if you want to think of that, the axis of symmetry. And in the xy plane, there's a circular cross-section of some kind. Then that means we can use polar coordinates for xy, using r is square root of x squared plus y squared, theta is inverse tangent of y over x, but just keep z, right? And then to go the other way around, we can say that, x is r cosine theta, y is r sine theta, and we'll just leave z alone. So basically, cylindrical coordinates is polar coordinates to replace xy, but leaving z linear, okay? When we do that, we get a cylindrical coordinate system. And so you would have your r dr d theta element, but then also times dz to make your dv element, okay? And it's really arbitrary which one is the circular cross-section and which axis is the axis of symmetry. So we express these formulas assuming that the polar coordinates will be done in the x, y, and the z is kept linear. But if you had some sort of a structure where, say, y was the axis of symmetry, you could either change all the letters, or frequently what people do is they just re-letter the whole problem. They just make the y as the z, and then make the z the y, so that we can just keep using these same formulas. So the actual letters used are arbitrary, but one axis is kept linear and the other 2 are converted to polar. And then that defines what's called cylindrical coordinates. Right, cylindrical coordinates are best for anything that, of course, has a cylindrical domain region, right? And we can just define z, so that's the one that is the cylinder's axis. It's also good for cones, because if you have a cone, then that means that even though it's not a constant radius, there is still a circular cross-section. Maybe the radius is changing as we go up in the cone, but cylindrical still works well for that. And also circular paraboloids. So if you're integrating over something where you have a paraboloid, right, that paraboloid also has circular cross-sections. It's just that the radius is changing in a nonlinear fashion, where it's changing in a linear fashion for cones. Okay, so all of those are where we would want to use cylindrical coordinates. All right. You can take the volume element of any extruded shape. We know is the base area times the height. So we said that it's just like saying well, it's like saying r d theta times an extra element for the height to make it a volume, right? But if you want to kind of picture what's going on, right, you have a change in radius, which is dr, and then you have an arc length here, which is r d theta, and then you have a height element, which is dz. So you have to multiply those three things together to form what is essentially a close to rectangular box that is dv. This element here is the volume element, right? So r dr d theta times dz is the dv element, okay? And then if you're going to convert to cylindrical, that means that whatever function you're given, if it's originally expressed in terms of x, y, z, you have to replace x's with r cosine thetas and y's with r sine thetas, and you leave z alone to convert everything in terms of these new variables. So basically we're taking a function which is a function originally, the multivariable output function of x, y, and z, and you have to convert it to be a function of r, theta, and z, right? Z is left alone, but x and y get replaced with new variables. So everything is substituted out. And just like always, you can specify any order that you want here, and anything can be dependent upon, like the inner limits of integration can be functions of variables that you have yet to integrate. Only the outermost one has to be constants. And that could be in any order. But very frequently, I would say most frequently, the z element is usually the one that's done first. And the theta element is usually the one that's done last. But there's nothing that says that has to be true. Typically it is in this ordering, but it doesn't have to be. All right, let's just do a few example problems just to see how this works. So this says, from the textbook, there's an example that says graph the point 2 pi over 3, 1, and then convert that to rectangular coordinates, which implies that this is cylindrical coordinates. So one thing you need to know that is that just like there's an ordering, right? When we have rectangular coordinates, we assume this is in the order x, y, z. When you have cylindrical coordinates, the assumed ordering is radius first, then angle, and then the z coordinate. So specifically in that order, radius, theta, z, right? So if I'm graphing that, maybe I could just graph that in 3 dimensions here. I'll draw a x, y, z coordinate system. Rather than convert it, let's just try to graph it directly from the cylindrical coordinates. So we're at a radius of 2 at an angle of 2 pi over 3. So the angle is from the x-axis. So if you were to go around 2 pi over 3, imagine that you have this thing going from 0 to pi, right, in the xy plane. 2 pi over 3 would be somewhere over here, right? So we're in this direction, right? And then we're going a radius of 2, so we're going to go 2 out along that direction, and then we're going to go up 1 in the z direction. So it would be a point somewhere there, okay, kind of in quadrant and octant 2. It would be on the other side of the yz plane from where we're looking. So that would be the point r 2 pi over 3, 1 in r, theta, and z in cylindrical coordinate system. Now the second part of this problem is asking me to convert this to rectangular coordinates. So that's easy to do because x is just r cosine theta. So that would be, the radius is 2 and the angle is 2 pi over 3. And I know from a unit circle that the cosine of 2 pi over 3 is -1/2. So that's going to be -1. And then the y would be r sine theta. So that's going to be 2 times the sine of 2 pi over 3, which I know that the sine of 2 pi over 3 is the square root of 3 over 2. So this is just going to be the square root of 3. And then the z is just the z, so the z stays at 1. So in the rectangular, this would be negative 1x square root of 3y 1z for the x, y, z coordinates to that same spot. So if you went, let me see, I don't really have another color here. I could use this, I guess. If I were to go, let's see, negative 1 in the x direction, and then the square root of 3 in the y direction, and then 1 in the z direction, I would get to that same location. Okay, so that's the idea behind cylindrical coordinates, and it does make integration easier in certain cases. So let's take a look. Oh, here's another conversion problem. Let's do this one first. Convert this, not graphing, convert this to cylindrical. So they're implying that this is rectangular. So I know that the conversions are r is x, x is r cosine theta, y is r sine theta, and z is z. The other thing is that x squared plus y squared equals r squared. So r is the square root of x squared plus y squared. And it's also true that since you have this relationship, the tangent of the angle is y over x, and so therefore the angle is the inverse tangent of y over x. So if I just wanted to find the r, I could just take the square root of the x squared and the y squared. So that's going to be the square root of 9 plus 9 is the square root of 18, right? Which I guess I could simplify that. If you're comparing this with the book, it's probably going to say that that's the square root of 9 times the square root of 2, which is 3 times the square root of 2. And then for the angle, it's going to be the inverse tangent of y, which is negative 3 over 1, which is 3. So the inverse tangent of negative 1. So thinking about a unit circle here, where is the tangent negative 1? So the tangent, we're really saying that the tangent of some angle is equal to negative 1. And the tangent we know is y over x. So y and x have to be the same except opposite directions. Tangents are negative here or here. And if the y and x are equal, they would be at these locations. So the angle is either 3 pi over 4, or it's 7 pi over 4, or it could be written as negative pi over 4. But the thing to know is that the inverse tangent function's its range, it can only output functions on this part of the unit circle. So we should report this as either negative pi over 4 or 7 pi over 4. So if I was going to write this in cylindrical coordinates, I would say that the r is 3 square root of 2, the angle is 7 pi over 4, and the z is still negative 7. Okay, that's the cylindrical coordinate equivalent. All right, and then let's do a couple of integration problems. Set up the integral for the triple integral xyz over some volume where E is a right circular cylinder with the z-axis as the axis of symmetry with a radius of 2 from z equals 0 to z equals 3. So let's try sketching that first. All right, xyz, we have z as the axis of symmetry, radius of 2 cylinder. Okay, so, and we start at z equals 0 down here, and then up here at z equals 3, there's another thing there. It's a right circular cylinder. I know it drew it kind of elliptical, but you have to imagine that's a circle. Starting at z equals 0, ending at z equals 3. Looks like we're just doing that. Set up the integral for this. Okay, so we'll set it up. The integrand is xyz. The dv element is r dz dr d theta. This can be in any order, but typically we do the z first, then the r, then the theta. So the z is going to start at 0 and end at 3. I think for all cases it's always from 0 to 3. There's no dependency there. The r is going to go from, so imagine now that on the outer integral you are on the xy plane covering a domain that has a radius of 2. We're covering this, and we're covering it with polar coordinates. So we're going to go from r is 2 to r is 0 to r is 2. And then for the the angle will just start at 0 and go all the way around until we get to 2 pi. So 0 to 2 pi. This would be the setup for doing this integration. Oh, wait, we're not done yet. Sorry, not done yet. Because we can't leave x's, y's, and z's in here along with the cylindrical coordinates. So we have to replace the x, y, and z with their cylindrical equivalents. So we would have 0 to 2 pi, 0 to 2, 0 to 3. The x would be replaced with r cosine theta. The y would be replaced with r sine theta. And we would have the z, which is just z. And then we would have r dz, dr, d theta. So that's the setup. And actually, if we were going to integrate this, this is separable because there's no dependency. Every single thing here is constant, which means technically if you were integrating it, you could do this. You could say 0 to 2 pi. If you were to integrate this, we have a cosine and a sine, d theta. And then we could maybe do the r portion, 0 to 2. And we have r times r times r, so there's a total of 3 r's. And then 0 to 3 for the z portion, and there's 1 z in there. But the answer to the question is really this. This is the correct answer, not this one here. Because you don't want to leave the x and y still in there when we're using cylindrical. All right. Okay, and then the last one, a little bit more involved, says find the volume of the solid that lies within both the cylinder x squared plus y squared equals 1 and the sphere x squared plus y squared plus z squared equals 4. So let's sketch what's going on here. We've got our coordinate system. I just start by sketching rectangular, and then I will convert in the integration process if necessary. We have a sphere of radius 2, right? So there's a sphere here, radius 2. But then inside there's a cylinder of radius 1, right? Where the axis of symmetry is z, because it goes forever in the z direction. There's a circular cross-section in the xy plane. So there's going to be something like this. A cylinder in here. Okay, that's not quite looking great, but you get the idea. A cylinder centered on the z-axis that has a radius of 1 inside a sphere centered at the origin with radius 2. And we want to find the volume that lies within both. So effectively, we are finding the volume inside this curved part at the top and bottom here, as well as everything inside the cylinder itself. So it does include these portions up here and down here, right? Okay, so let's see. We're going to cover that. Well, since we're finding the volume, the integrand is just going to be 1. We're not integrating anything else. We're just integrating space itself. So the integrand will be 1. And then let's see. The element is going to be r. Well, I think we're going to use polar. I think for sure, or cylindrical. So r dz dr d theta. Okay. And so for the z, we have to go from this boundary down here to this boundary up here, right? So that's established by the sphere. And we want to know where we start and stop in the z direction. So down here, well, if I solve this for z, I'm going to get z squared is 4 minus x squared minus y squared, or z is plus or minus the square root of 4 minus x squared minus y squared. So it looks like this bottom curve is going to be z equals negative square root of 4 minus x squared minus y squared. And then the top curve is going to be z equals positive square root of 4 minus x squared minus y squared. Okay, so I could go ahead and write that. Let me just write that like that. We have negative the square root of 4 minus x squared minus y squared to positive square root of 4 minus x squared minus y squared. Okay, and then for the r and the theta, I'm going to redraw the top-down view of the domain down there in xy, just the 2D part of the domain, which is, if you project it on the xy plane, It's this right here. It's a circle, right, that has a radius of 1, right, because the radius is 1 for the cylinder. And so we would be covering that with polar coordinates starting at r is 0 and ending at r is 1. So it's going to be from 0 to 1. And then we'll go all the way around the circles, so from 0 to 2 pi. So there's a setup that's partially done. The reason why it's not quite done yet is that we still have some x's and y's in here. So let's do this down here. Would you agree that I could say this is minus x squared plus y squared? And therefore, this is 4 minus r squared. So instead of leaving that as x squared minus y squared, let me write this not using x's and y's. And instead, we'll say negative square root of 4 minus r squared, positive square root of 4 minus r squared. Okay. Now this one didn't say setup only, so let's go ahead and evaluate this, see if we can do the evaluation. This is the setup. If we encountered this on a test and we said setup only, that would be the answer. You could change orders. I'm not sure there's an advantage one way or the other. Could we do these separately? I don't think so, right? Because there is some dependency here. The z here, it depends on r. So the z at least has to be done before the r, okay? So let's just do it iteratively. The first integral, the z integral, would be the integral from negative square root of 4 minus r squared to positive square root of 4 minus r squared. And it's just 1 r dz. Okay, so while we're treating z as the variable, the r is a constant, so that can come outside of the integral. You don't have to explicitly write that step, but you can. So the antiderivative of 1 is just the variable. So we have our constant r, the variable is z, from negative square root of 4 minus r squared to positive square root of 4 minus r squared, which means we have to have the two copies, this minus this, and we would be plugging in positive square root of 4 minus r squared here, and negative square root of 4 minus r squared there. So if we have this, these are going to cancel, plus plus, so in fact I have two of those. So I'm going to have 2r, and then the square root of 4 minus r squared, right? That's the result of the inner integration, the z integration. So now we'll move to the dr, and we're going from 0 to 1 dr. Okay, so the dr integral is from 0 to 1 of that, 2r. Good thing that we did that one first, because now we have the r we need to do integration by substitution. So let's actually narrate that a little better. So we're going to pull the 2 out. We have 0 to 1 r. And then let me write this as 4 minus r squared to the 1/2 power, dr. Okay, so I'm going to do a u substitution here. U is 4 minus r squared. Therefore, du dr is negative 2r. So du is negative 2r dr. So r dr is negative 1/2 du. So doing that here, I would have 2. I've got, this is now u to the 1/2, and the r dr can be replaced with negative 1/2 du. Okay, so then I have to figure out the new limits of integration. So when r was 0, u would be 4 minus 0 squared, or 4, so this would become 4. And when r is 1, u would be 4 minus 1 squared, so that would be 3. 4 minus 1 is 3. And then I'm going to do a couple more things before I actually integrate. When I bring the 1/2 out here, it's going to cancel. So this is going to be negative 4, 3 u to the 1/2 du. But if I change the order of integration, the negative goes away. So it's going to be the same as integral 3 to 4 of u to the 1/2 du. Now let's actually do the antiderivative. When you add 1 to that, you get 3/2. Dividing by 3/2 is 2/3. So 2/3 u to the 3/2 from 3 to 4. 2/3, and then I'm going to have let's see, 4 to the 3/2 power minus 3 to the 3/2 power. I would probably grab a calculator at this point, just to make sure I don't make a silly error. 4 to the 3/2. You know what? I think we're going to end up with square roots in here, so maybe not. Let me do this. What is that over on the side? What is 4 to the 3/2 power? Well, that's the same as the square root of 4 cubed. Would you agree with that? Right? So the square root of 4 is 2. 2 cubed is 8. Okay, but what is 3 to the 3/2 power? Well, that's going to be the square root of 3 cubed, right? That's one way to think of it. It's also 3 cubed and then the square root. So that's the square root of 27. I think I like that way a little bit better. So that means this could be 8 minus the square root of 27, okay, times 2/3. That's the result of the second integral. The third integral is 0 to 2 pi d theta. So that's not going to change anything because there's no dependency. Let me just switch back to blue. For d theta, we have integral from 0 to 2 pi of 2/3 8 minus square root of 27 d theta. There's no theta in there, so that's all just a big constant. So it's just 2/3 8 minus square root of 27 theta from 0 to 2 pi. So that's going to be 2 pi minus 0, so we just multiply by 2 pi. So we're going to get 4 pi over 3 times 8 minus the square root of 27. That is the final answer. All right, so doing the z first turned out to work out pretty well there. All right. All right, and that's where we're going to stop the lesson there. There's a lot of different things you can encounter, but we'll just encounter those in the homework. So give the homework a try and then bring questions to class.